All right, everyone. So I'm going to continue with chapter 22. So this is part 2 video. And we basically continue with some application of the magnetism. So remember one thing we talked about was that if there is a magnetic field, that means there's a region with magnetic field. So for example, here magnetic field into the board or into the page. Okay. And let's say we have a charged particle moving in that region. So let's say here's a charged particle moving that region with velocity v. So that's it. There's a magnetic field into the page. All right, so as this particle is moving in that magnetic field, because of the right conditions for us, that means velocity is non-zero, magnetic field is non-zero, and velocity and magnetic field not parallel to one another, there's going to be a force acting on this particle. Using a right-hand rule, you should be able to see that the force will be to the left. Again, fingers in the direction of the velocity, curl in the direction of magnetic field. So you're curling down, your thumb pointing to the left. So here's the magnetic force, which is going to deflect the particle like that. All right, so now, what if we, instead of a particle, have, collection of particles, right? So that's kind of what we're going to be considering in the next, let's say section, in this section. So let's say this magnet here gives us an external magnetic field. So that's the magnetic field you can see, right? Generated by the magnet. Okay, that means there's a magnetic field there. And there's a wire. Okay, so let's say kind of like, turn around a little bit. So in terms of like sort of like a 90 degrees. And what we have here is a region where there is a magnetic field into the board. And then there's a wire in that region, or at least, the parts of the wire, right? You can see, right? That part of the wire is in that region. So let's say that part is not in the region, so it's never going to be affected by that magnetic field. But this length L of the wire here is in that magnetic field, and it's going to be affected by that. All right. So let's see then what happens. If we start with, let's say, let's say case 1, where there's a magnetic field, external magnetic field, and there's a wire with no current running through it. It's like similar to having a charge there sitting, doing nothing. Okay. And if the charge is there doing nothing, right, which again, it's a very simplified because charge is technically moving there, but they're moving in such a random direction that you can assume that there is no collective motion of those charges. So no collective velocity of those charges. So then velocity here is 0. And then we know, right, if there is a velocity 0, there is no current, there is no magnetic force. That means this wire will not be affected at all, okay? So it will just remain vertical like that. And then what we do here is we turn on the current, and now you can see, right, there's a case 2 where there's an upward current. The upward current is, you can think of like generated by the moving charges in the wire, right? So remember, there are charges here. So kind of like, let me do it here so you guys can see sort of. Imagine now there are, some of those charges are given, remember, so technically there's a current because there's a potential difference between two ends of the wire, but they are given push upward. So then they're all going to be then moving upward. So now think like this. Here's then the velocity of those, all the charges, right? Remember, the current, nothing but the flow of charges. So now all those charges are moving upward. Again, right-hand rule will tell me that force due to the magnetic field, which is perpendicular to the velocity or perpendicular to the current, will be to the left. That means all of those charges now going to be acting, feeling the force to the left. Again, so this is assuming that, we're here now. So those charges are moving. So then this wire collectively then going to be pushed to the left. Okay. So it's going to be pushed to the left, but you can see, right, only in this region, because that's the region where there's a magnetic field. But again, using the right-hand rule, you can see, right, that if there is a, a current, so let's say, so these are your fingers, right, in the direction of the current. From the direction of the current. And then you're going to be curling inside, right, inward in the direction of the velocity, in the direction of magnetic field. Your thumb should be pointing to the left. So that means there is a force to the left. The next, case 3, we reverse the direction of the current. Now current going down. Again, if the current going down, now you can think of like there are the charges that going down, some positive charges going down. And again, using right-hand rule, you should be able to see that if your fingers in the direction of the velocity, then they have to be curled downward in the direction of the magnetic field. Then in this case, your thumb is pointing to the right. So there is a force acting on this wire to the right. Okay, so that's kind of like the idea of it. So that's why you can see that the wire is actually bent toward right. In the case 2, right, the wire is bent toward left because of the force acting due to this external magnetic field. All right, so magnetic field is into the page, the current upward along the page, the force is to the left. Summarize that, right? So the field is into the page. So this is basically case 2, right? So this was like what I explained as case 2. That means magnetic field into the page, current upward, forces to the left. The next one, which was case 3, magnetic field into the page, current down, the forces to the right. Okay. Obviously, you can have other way around too, right? So you can have case 3 as like case 4, where the magnetic field is out of the page, current up, and then 5, which is magnetic field is out of the page, current down. So, but you're going to see that you can use right-hand rule to get those other, let's say scenarios as well. All right, so as I mentioned, right, so we can consider current as the collection, of charges all being, moved in the same direction. Remember, they are being pushed inside the wire due to the electric field, right? So electric field due to the battery, right? So generate, let's say this electric force on those charges, so they're moving inside the conductor. But because there's a, let's say this region, there's a region there with the external magnetic field, well, and this wire has a magnetic field and motion of the charges such that they are perpendicular to one another, or at least they're not parallel to one another, right? In that case, you're gonna have a magnetic force. Again, you can see, right? Magnetic force, velocity perpendicular. Magnetic force and, the magnetic field. So magnetic force and velocity perpendicular, magnetic force and magnetic field perpendicular too, because magnetic field is into the page and force is upward. So that's kind of what we have. So remember, this is the equation for a single particle. That's for the single particle. And what we have here is we have, a collection of particles, right? So for example, what I can do here is I can say, all right, so since this is the region where there's a magnetic field, I can look at in terms of sort of like, let's say, a volume of interest where the charges are moving, right? And that volume pretty much, kind of like, so this kind of represents that. And so this lowercase n is equal to number of particles per unit length, right? So, and you kind of like can then, represent this together, right? Put them all together into this equation where you have, sorry guys. Well, yeah, so let's say you're saying that this is QV cross B is for the single particle, and then n number of particles, right, saying that volume, right? And then you can say that, okay, so the lowercase n is equals to number of particles per volume. So that's kind of like per, for volume, that means area times length. Okay. And that's why then you rearrange then the number of particles in that volume is equals to n, which is the concentration times AL. So that's why, this N times AL replaces the number of particles, so that your equation ends up like that. Okay. All right, so we talked about this in circuits, right? So where N is the concentration number, okay? All right, so then if I kind of rearrange this equation, right? So if I combine some of those things, so if, for example, if I go and combine some of those quantities together, so for example, so here if I do the N A Q V, so that together cross, let's say B, right? And then let's say there's a L. So that together is what we defined to be current in the previous chapter, okay? So that's why what I can do, I can replace that with the current here, okay? So the length element stays, magnetic field stays, and the cross product going from the velocity cross magnetic field becomes the length element of the wire cross magnetic field. That means if you have a current carrying wire, okay, so if you have a current carrying wire, then, so let's say there's a magnetic field in this region. So what you do here is you take this length, so this is the length, right? So some kind of length vector, right? And the magnetic field vector, and then do the cross product between them, because cross product has to be between two vectors, and current is not a vector, so we cannot do a cross product between them, right? So, but we can do that, right? So we can say, okay, so the magnetic force on that wire due to the external magnetic field is the current in the wire, then length of the wire that is inside that magnetic field cross the magnetic field, okay? So which in a way will be, let's say, IL B sine of, let's say, phi, right? Where L is the distance, distance of interest or the length of interest, and the magnetic field magnitude and sine of angle between the wire and the magnetic field, okay? So for example, let's say here's your magnetic field, and let's say here's your wire. That means this is a current, so this was the magnetic field. So this is then phi over there, okay? So if it's a uniform magnetic field, and let's say you have this length L, right? And the angle phi between current, or the length L, remember this is length L, which is basically the same direction as the current, right? It's a straight wire. That means if it's a straight current carrying wire, that's the equation for that. Okay, it's relatively simple if it's straight current carrying wire. Okay, it becomes a little more difficult when the wire is not straight. Let's say you have something like this, okay? Then what you have to do is, you can see, right, compared to before, for example, if I have a wire like this, see every part of the wire, let's say here's, if I talk about every part of the wire has this length L, right, or the small length L, they all have the same, angle with respect to the magnetic field. But if you have the wire like that, that's different, because small element here has a different phi. Small element here is different one. This one here is a different one. This one there has different one, right? So the phi basically changes. Well, in that case, we cannot assume that, let's say, our magnetic force, so we cannot say that, we can just use, ILB sine of phi, because, that's no longer, can be applied because it's not a straight current carrying wire. Then what we do here is we just take a small little element, ds. This is the length element. Again, so we don't have this, right? So let's say this is more general. So small little element ds. And then we find the magnetic force that only on that small element, ds, which will be in terms of d, that means small element magnetic force equals the current through the wire, that length of that segment of interest cross p, okay? And then what we do here, we just take the, integral of both sides. The left side just becomes magnetic force. The right side is the current constant, so doesn't matter. So the current, assuming that's not changing current because it's a scalar quantity, comes out of the integral. So, but we have then ds, which is the small element length, cross the magnetic field. And this is basically going from, you integrate going from this point A to that point B, right? Because what we can do here is break it down into very, very many, like let's say small elements, and then find that contribution and then add them all together, which is basically what we have the integral for. Anyway, so that means this is the general equation, right? So this is the general equation. So that's why, for example, if it's a straight current carrying wire, right? So let's say here's a straight current carrying wire, and where then this element, ds, or you can think like the idea is that for this straight current carrying wire, the magnetic field is uniform for all of those elements. So in that case, I can have f of b is equals to I integral going from point A to point B. Since magnetic field is constant for all of them, it can come out. So then becomes, or you can say that this just becomes, B ds sine of phi. All right. And then this becomes I B, and again, let's say sine of phi, then integral of ds from A to B. And that's nothing but the length, right, between those, let's say, 2 points. Again, I'm deriving for the straight current carrying wire. So you can see it becomes I, this integral gives you just a length L, then magnetic field B, then sine of phi angle between them. So that's why this is the general equation that I can use for the simple straight current carrying wire, or much more complicated segments, or maybe like, let's say, maybe like a circular, some kind of, that we're going to see an example, right? So, but you always start with this equation, and then you can simplify the way you want. All right, so here's an example. You have a wire bent into a semicircle of radius r, forms a closed circuit, and carries a current I. Right. So the wire lies in the XY plane. Okay. And the uniform magnetic field is directed along the positive Y axis. Find the magnitude and direction of the magnetic force acting on the straight portion of the wire and on the curved portion of the wire. Okay. So that means, wire goes around, right? So the wire goes like as a curved portion, right? So semicircle, and then a straight portion. So we're going to divide this into 2 segments. Okay. So you can do like, here's segment 1. All right. So here's segment 1. And this one here is segment 2. Okay. Semicircle. Okay. So let's look at first, this segment 1, which is the straight part. Okay. So that one is, in terms of, you can see, right, I have sort of like, let's say, coordinate system, where my coordinate system is, I take the center here as my origin, and then let's say, you can see, right? So that means, let's say this will be radius going from here to there. So that's a radius r. But what also means that this is also same size or same distance. That means it's also a radius. But that means I can say that this segment, right, goes from negative r to positive r, right? So my segment, right, that straight segment goes from negative r to positive r. Okay, so again, I'm going to consider this as my first segment, and this one, the curve, is my second segment. All right, so let's find the force for the first segment. All right, so using the equation for the force, where this is equals to current times going from point A to point B, then ds cross B. That's my general equation. Okay, so what I have here is, so I have magnetic field, okay, and magnetic field is, can't say, right, this is by j hat, right? Magnetic field is by j hat. And let's say any small element that I choose, so let me do it kind of here, right? Any small element that I choose, right? So this is, let's say, my ds. Okay, so you can see, right, ds is nothing but, dx I hat, right? Because it's a horizontal, it's in the horizontal direction. So I can say it's like, horizontal. So ds is just dx, and I hat is, that is pointing to the right. okay? So I can basically just do that. All right, so that means this, can be changed into, okay, so it's a current. Okay, so point A is negative R, point B is positive R. And the inside, right, so this guy becomes, ds is dx I hat, then cross, then magnetic field is by j hat. Okay, or you can just say bj hat, right? We know it's bj hat. Okay, well, this then becomes current times negative R to a positive R, and here B, and let's say dx, right? Because dx and B can be combined. And then what you do here is you're doing then the cross product between those two unit vectors, I hat and j hat. And you are going from I hat to j hat. So if you use your right-hand rule, you can say, right, I hat cross j hat gives you k hat. Okay, k hat. And then from here, what I have here is that current is outside already, magnetic field is uniform, can come out already. And then I have negative R to positive R, just dx. Okay, and even like, let's say, k hat can come out as well. Okay, well, I, B, k hat, and if I'm integrating that, that's just basically just x, right? X from negative R to R. So then I have then I, B, k hat, so R minus negative R. And you can see that force for the segment 1 is then nothing but 2 times the current times the R, because R minus R gives you 2R, right? So 2IRB k hat. That means force due to this straight segment will be in a k hat direction, which is out of the board. And that is the magnitude, 2 times the current times radius times the B. So here's the magnitude, and then k hat is the direction. The next is for the curved portion. Okay. Now, for the curved portion, then we are using this ds, right? So we can then take that one. So it's a little more complicated because it's a curved one, right? So then you can see, right, there's this, there's this angle theta, right, with respect to my ds and let's say the magnetic field, okay? So then what I can do from here is, let's say if I'm looking at this contribution to the curved part, which is the second segment, so then I have I ds cross B, okay. Then I can see that what I have to deal with here is the component, right? I have to deal with the component of that. I have to deal with the component of the, my ds. So which basically becomes I, B, I'm gonna do it like this. So I, ds, sine of theta, but let's say in that case, obviously, times B, right? Remember, if you have the ds, if you have the B, and then there's sine of theta, right? We can kind of write it like that. And what I have here is, so this ds component, right, that I'm going to be considering here, that's the component, right? So you can see, right, that's the component that I'm considering is opposite. So that's why I end up with a sine of theta over there. So that's, in the negative I hat, and then the magnetic field here is in a j hat direction. So I have that cross product. Okay. So, this is before I do the integration because I'm still using df2 over there. So then I'm going to have I times ds times sine of theta. And when I do this cross product, I'm going to get negative k hat. Okay. That means here, what I have is negative I ds sine of theta k hat. All right, so that's just for this tiny ds, and that means then I have to integrate to get the total. So then I have f2 is equals to, so then I have then negative I ds sine of theta k hat. Okay. Now, what I'm doing here, you can see, right? I have over here ds, and I have over sine of theta, and obviously I have the theta that is changing, going from here to there. Okay. So there are two things I can do. I can either leave it in terms of ds and do as a circumference, half a circumference, or I can actually do this, substitution. I can say that ds is equals to r times d theta. Remember, this is just the arc length. Sorry. Well, it doesn't allow me. So arc length equals r times theta, right? And if you're doing ds, then this becomes d theta. So that's what I'm doing. So I'm going to replace ds with the r times theta. So negative current can come out, r, let's say in this case, I think I forgot magnetic field over there. So magnetic field, then sine of theta, sorry. I'm going to remove this out of the, so k hat, and then inside the integral, then I have sine of theta, but then ds is replaced with r d theta. I can take r out of the, integral as well, and now I'm doing the sine theta d theta. Okay, and what I'm doing the integral here is from point A to point B, which is nothing but going from 0 to pi. Okay. All right, so if I do this integral, I'm gonna, integral of sine of theta, here is negative cosine theta. And so let's say what I will get from here is negative I R B, then negative cosine theta from 0 to pi, direction k hat. Again, if I plug in all those, the value of pi and value of 0 and do the calculation, what I will get is negative 2 I R B k hat. And that's the answer for the force for the second segment. Right, so you can see, right, a little bit more complicated derivation because it's a curve and you are dealing with the component. Remember, I could not use the parallel to the magnetic field component of the ds because, the parallel component, doesn't feel. So for what I mean here is this, right? So see, like this ds, I break it down into two components, okay? And what I had to do here is use this component over there because this component is perpendicular magnetic field. This second component is parallel to magnetic field. And that doesn't, work. That means you cannot have a parallel component to magnetic field because, remember ILB sine theta, right? So L and B cannot be parallel. Otherwise, there is no magnetic field for that portion. All right, so that's why I have to use this component, which is basically, give me ds sine of theta. That's where it's coming from. Okay. All right, so we can also have a rectangular loop, which carries a current I in the uniform magnetic field. So let's say there's some kind of uniform magnetic field, some external magnetic field in that region. And I have it in a loop, rectangular loop. And there's a current counterclockwise, okay? So that means my loop has side A, on, a vertical A, and let's say horizontal side B, okay? And no magnetic force acts on that side, okay? So what I have here is this. So let's say I have to break it down into 4 segments. So I have, like, let's say segment 1, segment 2, segment 3, and segment 4. And I want to look at where do I get magnetic force? Which segment actually will have magnetic force acting on it and which one will have 0 force? Because one of the things you will see here is there are some of the segments will have no force acting on it, because remember the equation was this is you can consider as a straight wire. So magnetic force is I L cross B or IL B sine of theta. And remember, so f of B is always 0 when L is parallel to B. Okay, so let's see. I have force for segment 1 plus force for segment 2 plus force for segment 3 plus force for segment 4. Okay, and you can see, right, I can basically completely ignore segments, so let's say segment 1 and segment 3. Why? Because if I'm considering, let's say if I'm considering segment 1, so that my ds component or L component, right, will be, 180 degree with respect to magnetic field. Sine of 180 is 0. And if I'm considering segment 3, my dl, ds component, right, or the L component, doesn't matter, right? So is 0 degree with respect to the magnetic field. So again, sine of 0 gives you 0. So this is 0 and this is 0. So you can see, right, then all I have here is segments, 2 and 4. So there's a magnetic field over there, okay? That means, I have to consider that, the orientation of the, current or orientation of the wire with respect to the magnetic field. So that's why wires are parallel to the field and cross product is 0, okay? So that means segment 1 and 3 have 0 magnetic force because the cross product is 0. But there's a force on sides, segments 2 and 4, all right? So they are perpendicular to the field, and because they are perpendicular to the field, there is a magnetic force, okay? But we can also look at in terms of in which direction is the force, okay? So for example, if you look at, so let's say here's segment 2. Remember, the idea here is the current going down in segment 2. Remember, there was a magnetic field like that. So let's say like that. For segment 2, then if I choose this direction for my, ds segment, okay, and if I apply that equation for the force, then I can see that there is going to be a force acting on it because those two are perpendicular to one another, okay? And there is going to be a force where I am doing, let's say let's say this is negative j hat, this is I hat, right? So there's going to be force acting on it, okay? So let's say if I'm doing the force will be out of the page, okay? Force will be out of the page. Hopefully you guys will be able to use your right-hand rule to figure this one out. And then if I'm considering then the segment 4, right? So then over there, my ds is up, magnetic field is to the right. Then this one gives me, magnetic force into the page, okay? That means the magnitude of the magnetic force on this side will be, from the equation, right? So the force is equals to ILB sine of theta, but ds or L, L and B are perpendicular, so it's just, ILB, okay? But remember, this side had a, we say that this is A, so that means the magnetic force for both of those will be, taking L is equals to A, so IAB, and that's what I have, right? So F2 and F4 have magnitude, current times length times magnetic field. So I times A times the magnetic field B. All right, so, but as I showed you, right, the directions are different. The F2 is out of the page, F4 is into the page, okay? And, they don't cancel. I mean, if you kind of look at net force, technically net force is canceled, okay? But there was something else over there, okay? There's something else we can have. Okay, again, so direction of F2 is out of the page, direction of F4 into the page, okay? Now, one of the things we can have here is then, because those are connected to each other, right? and maybe we can have this fixed at the center at some point, then we can have a rotation, okay? You can see, right, with respect to this pivot point, then let's say point 2 has an upward force, segment 2 has upward force, segment 4 has downward force, and that's gonna make it rotate clockwise, okay? The forces are equal in opposite direction, but not along the same line of action. So there's a torque, right? There's a torque with respect to that point O. Remember, so the equation for torque was force times R, right? And you can see that if you're talking about that, so this was length B, and both of them have a B/2 distance with respect to the pivot point, okay? So then I can say that force 2 times distance, B2, plus force 4 times distance, B2 again, and then we have AIB times, this is the force, times B/2 distance, plus another force, B/2 distance, then we get current times AB times, magnetic field, right? So why are we adding them together? Well, remember, even though one is up, the other one is down, when you're considering torque, they both give you the same rotation, right? They both clockwise. So just take clockwise positive and just, add them together, right? So that means you're still, adding them together because both give you the same directional rotation. All right. So that's kind of, what we can get from here. That means maximum torque, okay? So you can see, right, this AB here is nothing but the area of that, loop. So then maximum torque is given as the current times area times magnetic field, okay? But, torque, remember, was a vector. So then technically, one of the things we have here is there is a vector version of this equation, which is current times area, which is area vector. So let's say if this was your loop, right? So let's say this was magnetic field. I can do it like this, right? So remember, the area is taken as vector area that has magnitude A, but is normal to the plane of the area, right? Plane of the loop. So then you do A cross B. Okay, so the area of that, area vector, right, cross the magnetic field B. So then this will give you then the, let's say, the torque. Obviously, one of the things we can have here is this equation can also be I times the area times B times sine of phi. For example, if here's the magnetic field, but